Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Look at the clock on your wall right now. Or, check the time on your phone, or just glance at the watch on your wrist.
Yeah, take a second to really look at it.
Because every single time that second hand ticks forward, or that digital number rolls over, well, it's lying to you.
Completely lying. And it's funny because we all share this incredibly deep, almost unquestionable intuition about what those numbers mean.
Right. We go through our entire lives operating on this assumption that time is a universal river.
Okay.
And you, me, the listener, we are all just floating in that exact same river, being carried downstream at the exact same speed.
Exactly. I mean, the fundamental assumption of human existence is that a minute for you, sitting right there right now, is exactly the same as a minute for someone making coffee on the other side of the planet, or a minute for an astronaut orbiting the Earth.
It's just a given. But that intuition is...
It's mathematically and observably wrong. The universal river of time is just a localized illusion.
Wow. Okay, so this isn't some abstract, philosophical wordplay. You were saying that our literal physical understanding of time, this master clock we think is ticking away in the background of the universe, is just broken.
Completely shattered. Yeah. I mean, the concept of a single, steady master clock governing everything everywhere, it simply does not exist. Time is local.
Local?
Yeah, it's malleable. It does not flow at the same rate for all observers. The actual fabric of time stretches and compresses, depending entirely on two things.
Okay, what are they?
How fast you're moving through space and how deep you're resting within a gravitational field.
Okay, let's unpack this, because this means we are talking about the literal structural source code of reality here.
We really are.
We're exploring how Albert Einstein realized the universe was playing this massive trick on us, and how this totally counterintuitive physics is secretly the engine running our modern world right now.
Yeah, and why the whole concept of now, like this specific moment you and I are experiencing, might actually just be a psychological hallucination.
Which is terrifying and fascinating, because we are talking about cold, hard, measurable facts today.
Absolutely. If you take two identical clocks, right? Synchronize them perfectly so they tick in absolute unison, and then you just put them on different paths through space-time, they will diverge.
Like they will physically show different times when you bring them back together.
Yes. And neither clock is broken. Neither has a mechanical flaw. They just traveled through different densities of time.
Different densities of time? That's such a wild phrase.
And
this has been tested, right?
Oh, tested and confirmed by experiment after experiment for over a century. And honestly, if we didn't mathematically correct for this warping of time every single second of the day, our 21st century infrastructure would literally tear itself apart before lunchtime.
Okay, so to really grasp why that clock on the wall is feeding us a localized fiction, we actually have to stop looking at time, right? We have to look at light.
Yeah, because to understand how time bends, you have to establish the one thing in the entire universe that refuses to bend.
The speed of light.
Exactly. So to trace that realization, we really need to go back to 1905, to the first of Albert Einstein's two big breakthroughs.
Right, his paper on special relativity.
Yeah. At the time, physics was still living in the house Isaac Newton built. Newtonian physics assumes space is just an empty, static stage, and time is the unchangeable clock on the wall of that stage.
And Einstein basically took a sledgehammer to that.
He really did. He looked at objects moving at constant velocities, and he built his entire theory on a single uncompromising rule. The speed of light in a vacuum is exactly the same for all observers, no matter how fast the light source or the observer is moving.
Okay, on the surface, if you don't know the physics, that sounds kind of mundane. Light goes fast, and it always goes the same amount of fast.
Right, it doesn't sound revolutionary.
But let's map that onto how everyday objects work, because that's where the absolute absurdity of Einstein's rule kicks in. Think about a highway. If I'm driving down the highway at 60 miles an hour and another car passes me doing 70, my perspective from the driver's seat is that the passing car is only creeping ahead of me at 10 miles an hour.
Exactly, because velocities are additive and subtractive.
Right. If I throw a baseball at 100 miles an hour out the front of a train that's moving at 100 miles an hour, someone standing on the platform sees that baseball traveling at 200 miles an hour. That makes logical sense to us.
Because the human brain relies on Galilean relativity, that simple addition of speeds. But light completely refuses to play by that rule.
So how does light behave in that scenario?
Well, imagine you're flying in a hyper-advanced spaceship at 99% of the speed of light.
Okay, moving incredibly fast.
Right. And you shine a flashlight at the front window. That beam of light does not travel at 199% of the speed of light relative to someone watching you.
Because there's a speed limit.
Exactly. But it also doesn't just pull away from your ship at a mere 1% of the speed of light, which is what the highway logic would suggest.
Right, 70 minus 60 is 10. So light speed minus 99% should be 1%.
But it isn't. From your perspective inside the ship, that beam pulls away from you at exactly the full speed of light.
Wait.
And from the perspective of someone standing still on a planet watching you fly by, that exact same beam of light is also moving at exactly the speed of light.
Okay, so this is the exact moment the universe backs us into a mathematical corner. You have two people moving at vastly different speeds, observing the exact same beam of light, and they both measure it moving at the exact same speed relative to themselves.
Yeah, which should be impossible.
Right. To make that true, the universe has to cheat. It has to alter something else to keep the speed of light constant. Let's walk through the light clock thought experiment, because visualizing the geometry here is really what finally made this click for me.
The light clock is perfect for this. It strips away all the mechanical complications, gears and springs. Just imagine the simplest possible timekeeping device.
Okay, I'm picturing it.
You have two highly polished mirrors facing each other, one mounted on the floor and one mounted on the ceiling directly above it, and a single pulse of light is trapped between them, just bouncing endlessly up and down.
Got it. And we define one tick of this clock as the time it takes for the light pulse to leave the bottom mirror, hit the top mirror, and bounce back down.
Exactly. Up and down tick, up and down tick.
Okay, now let's take this light clock and mount it inside a transparent spaceship. And that spaceship is going to fly past me at a massive velocity, let's say half the speed of light. I'm standing perfectly still on an asteroid, watching the ship zoom by from left to right.
So let's isolate the perspectives here, starting with the astronaut inside the spaceship. From their point of view, they're perfectly stationary inside their cabin. The floor is below them, the ceiling is above them. They watch the light clock, and they see the pulse of light traveling perfectly straight up and perfectly straight down.
So the distance the light travels for one tick is just twice the height of the cabin.
Right. Simple. But your perspective, standing outside watching the ship fly past, is entirely different.
Because the ship is moving.
Yes. When the light pulse leaves the bottom mirror, the ship is at, let's say, position A. But by the time the light travels up to hit the ceiling mirror, the entire ship has moved forward to position B.
Oh, right. So from my vantage point outside, the light pulse didn't go straight up. It had to travel diagonally forward and upward to catch the moving ceiling mirror.
Exactly. And the geometry continues on the return trip. By the time the light bounces off the ceiling and returns to the floor mirror, the ship has moved even further forward to position C.
So the light has to travel diagonally forward and downward.
You got it. From your stationary perspective outside the ship, the light pulse isn't moving in a vertical line at all. It's tracing a zigzag pattern, a series of long diagonal lines through space.
And here's where the trap closes on us. Because basic Pythagorean geometry tells us that a diagonal line connecting two horizontal points is always physically longer than a straight vertical line between them.
It has to be.
So the path the light took from my perspective outside the ship is a definitively longer distance than the path it took from the astronaut's perspective inside the ship.
And this is where we apply Einstein's unbreakable rule. And the equation for speed is universally simple, right? Speed equals distance divided by time.
Right.
We've established that the distance the light traveled from your perspective is greater than the distance it traveled from the astronaut's perspective. But the speed of the light cannot change. It must be identical for both of you.
Right. So if the distance is a larger number for me and the speed is locked as a constant, the math physically forces the time to be a larger number too. The only way to balance the equation is if the time it took for the clock to tick was literally longer for me than it was for the astronaut.
The inescapable mathematical reality is that the moving clock ticks more slowly than the stationary one. From your perspective, looking into that moving ship, time itself is dragging. The physical progression of reality has slowed down to compensate for the longer distance the light had to travel.
just to ensure the speed of light remains perfectly constant.
Yes. This is special relativistic time dilation.
I always try to find the trick here. To say, well, it's just an optical illusion. The light is just taking longer to reach my eyeballs because the ship is moving away. But that's not what's happening, is it?
No, not at all. The actual biological aging of the astronaut, the decay of atoms in the ship's hull, the thoughts firing in the astronaut's brain, every single localized physical process is happening in slow motion relative to the rest of the universe.
It's a genuine asymmetry in the fundamental rate at which reality unfolds. It's not an artifact of observation.
Right. Observers in different states of uniform motion experience different intervals of time between the exact same events.
But the immediate counterargument anyone would have is, okay, if motion slows down time, why don't I experience a time warp when I merge onto the interstate? Like, why don't my watch and my car's dashboard clock stay perfectly synced?
Well, the physics is governed by a mathematical term called the Lorentz factor. And this factor dictates exactly how much time dilates, how much length contracts, and how much mass increases as an object's velocity approaches the speed of light.
Okay.
And the key to understanding why our daily lives feel strictly Newtonian is the shape of that Lorentz curve. At the relatively sluggish speeds humans travel at walking, driving a car, even launching a rocket into orbit, the velocity is such a tiny fraction of the speed of light that the Lorentz factor remains incredibly close to 1.
Meaning the time dilation multiplier is basically like 1.000000001. It's so infinitesimally small that it completely falls beneath the threshold of human perception.
Exactly. To put a number on it, if you board a commercial jetliner and fly at a cruising speed of roughly 1,000 kilometers per hour, you are absolutely experiencing special relativistic time dilation.
I am.
Yes. But the amount your local time slows down compared to someone on the ground is measured in a few nanoseconds per hour.
A nanosecond being 1/1000th of a second.
Right. So the biological difference is practically non-existent to our senses.
But the Lorentz factor isn't linear, is it? It's an asymptote. When we start pushing the velocity higher, the math stops being a rounding error and becomes violently dramatic. Let's say we finally invent a propulsion drive that can push a spacecraft to 90% of the speed of light.
At 90% of the speed of light, the Lorentz curve spikes sharply. Time for the crew on that ship would run at less than half the rate of a stationary observer on Earth.
So for every hour that ticks by on the ship's clock.
More than 2 hours pass for mission control back home.
Wow. Let's push the engines to 99% of the speed of light.
At 99%, the dilation becomes severe. Time on the ship runs at roughly 1/7 the normal rate. If the crew spends a single year traveling at that speed, 7 years will have evaporated on Earth.
What about 99.9%?
The closer you shave the margin to the absolute speed limit, the more extreme the temporal distortion gets. At 99.9% of the speed of light, time slows to about 1/22nd of the stationary rate. The denominator in the Lorentz equation shrinks toward 0, which means the time dilation factor explodes toward infinity.
And if we somehow breach the limit, if we hit exactly 100% of the speed of light,
If an object with mass could somehow reach the exact speed of light, the mathematics dictate that time would stop entirely.
just freeze.
The internal clock of that object would freeze. I mean, think about a photon. A photon is a particle of light, so it naturally travels at the speed of light. It essentially experiences no time.
Wait, really? No time at all?
None. From a photon's perspective, the moment it is emitted from a star and the moment it strikes your retina millions of years later happens simultaneously.
That is mind-blowing.
But for anything with mass, a human, a spaceship, even a single proton reaching the speed of light is physically impossible. As the Lorentz factor approaches infinity, the energy required to accelerate the object also approaches infinity. The universe forbids mass from reaching the speed limit.
This all sounds like a brilliant piece of chalkboard theoretical physics. But what blows my mind is that physicists didn't just leave this as a mathematical curiosity, they actually found ways to physically prove it. I mean, I know there was an experiment in the early 1970s, the Haffel-Keating experiment.
Yes, a classic.
Where they supposedly put atomic clocks on commercial airplanes. But my first thought when I read about that was, how could a normal passenger plane, flying at maybe 600 miles an hour, possibly go fast enough to measure an effect that requires the speed of light to become obvious? Weren't they just flying around the world on standard Pan Am flights?
You're right to be skeptical because, as we established, passenger jets are crawling compared to the speed of light. The time dilation at those speeds is incredibly minuscule. But the brilliance of the Hafele-Keating experiment wasn't in the speed of the planes.
What was it?
It was in the sheer, unfathomable precision of the instruments. In 1971, Joseph Hafele and Richard Keating took 4 cesium beam atomic clocks. These are devices that measure time by counting the exact microwave resonances of cesium atoms. They're so precise they might lose or gain a single second over tens of millions of years.
So they took these ultra-sensitive instruments, literally bought them passenger tickets, and strapped them into the seats of commercial airliners.
Literally. They flew one set of clocks eastward around the world and another set westward around the world. And meanwhile, they kept a reference set of identical atomic clocks completely stationary at the United States Naval Observatory.
Okay, so the goal was to see if the flying clocks, having experienced the velocity of the airplanes, would physically disagree with the stationary clocks when they got back. But why eastward and westward? Does the direction matter when you're just measuring speed?
Oh, it matters immensely because the Earth itself is spinning. The stationary clocks at the observatory are already moving because the surface of the Earth is rotating.
Oh, right.
When the plane flew eastward, in the same direction as the Earth's rotation, its velocity added to the rotational speed of the Earth. It was moving faster relative to the center of the Earth than the stationary clocks. Therefore, special relativity predicted the eastward clocks should run significantly slower and lose time.
And the westward flight was flying against the rotation of the Earth, essentially subtracting from that rotational speed. So relative to the center of the Earth, the westward plane was actually moving slower than the stationary observatory on the ground.
Exactly. The mathematics predicted a very specific tiny discrepancy for both journeys. And when Hafele and Keating brought the flying clocks back into the lab and compared the readouts to the reference clocks, the numbers did not match. The eastward clocks had lost time. The westward clocks had gained time. The physical time displayed on the instruments was fundamentally different, and the discrepancy perfectly matched the nanosecond calculations derived from Einstein's equations 50 years prior.
They physically carried a slice of reality into a different temporal flow, let it steep there, and brought it back. That is profound.
It's incredible.
But there's another real-world proof of special relativity that is even more dramatic, because it doesn't require man-made atomic clocks, right? It happens naturally, millions of times every single second, right above our heads in the atmosphere. The muon survival test.
Yes. The behavior of muons is a continuous, naturally occurring demonstration of time dilation. Particle physicists rely on it daily. To understand it, we have to look at the upper limits of the Earth's atmosphere. Deep space is filled with high-energy cosmic rays, mostly protons, traveling at immense speeds. When these cosmic rays slam into the molecules of oxygen and nitrogen in our upper atmosphere, the violent collision creates a shower of secondary subatomic particles. And among these are particles called muons.
So these muons are born high up in the atmosphere, maybe 10 miles above the surface, and the momentum from the collision sends them hurtling downward toward the ground at velocities incredibly close to the speed of light.
Correct. But the muon has a fatal flaw. It's a highly unstable particle. Once a muon is created, it has an incredibly short half-life of roughly 2.2 microseconds.
That's 2.2 millionths of a second.
Right. After that microscopic flicker of time, it decays into an electron and a couple of neutrinos. It ceases to exist as a muon.
Wait, let's look at the math there. If a muon only lives for 2 millionths of a second, it shouldn't be able to survive the trip to the ground. Even if it's traveling at 99.9% of the speed of light, the atmosphere is miles thick. Light itself takes significantly longer than 2 microseconds to travel 10 miles.
It does.
If time is a universal constant ticking away at the same rate for everything, every single muon ever created should die miles up in the sky. Yet we have detectors on the surface of the Earth and even deep underground in mines that are constantly being pinged by intact muons. How is that possible?
This is the exact paradox that makes time dilation an undeniable physical reality. If the universe operated on Newtonian time, the probability of a muon reaching the surface would be functionally zero. But we detect massive swarms of them.
So how do they make it?
To resolve the contradiction, you have to look at the journey from 2 completely different reference frames. Let's start from our perspective, standing on the Earth next to our muon detector.
Okay, from my perspective, I'm stationary, and the subatomic particle is rocketing toward me at 99.9% of the speed of light. Because it's moving so incredibly fast relative to my frame of reference, the Lorentz factor is huge. Special relativity dictates that the muon's internal clock, the rate at which it experiences its own decay process, must be running exceptionally slowly.
Exactly. While the clocks in our laboratory are ticking away at a normal speed, the muon's biological clock, so to speak, is barely advancing. From our perspective, that fleeting 2-microsecond lifespan is violently stretched out.
So it lives longer.
Yes. It's dilated by a factor of perhaps 50 or 60, depending on its exact speed. Because its time is running in extreme slow motion, it easily survives the 10-mile journey down through the atmosphere before its internal clock finally reaches the 2-microsecond mark and it decays.
That perfectly explains why we see them hit the ground. But the rule of relativity is that there's no preferred frame of reference, right? What happens if we try to imagine this from the muon's point of view? Because in the muon's frame of reference, it isn't moving at all. It was born, it's sitting completely stationary, and it's the Earth that is rushing up to hit it at 99.9% of the speed of light.
And that is a perfectly valid physical perspective. In the muon's stationary frame, its internal clock is ticking normally. It does not experience time dilation. From the moment it is created, it only has 2.2 microseconds to live, period.
But if it only lives for 2 microseconds in its own reality, how does it physically cross 10 miles of atmosphere before it dies?
Because of the necessary mirror image of time dilation, length contraction.
Length contraction.
Space and time are not separate entities. They are interwoven into a single 4-dimensional fabric called space-time. When you move at relativistic speeds, time dilates, but the physical space along the direction of motion contracts. From the muon's perspective, the Earth is rushing toward it at near light speed. Therefore, the physical distance of the Earth's atmosphere is severely length contracted.
So the 10 miles of atmosphere literally shrinks.
To the muon, the atmosphere is not 10 miles thick. It is compressed down to a fraction of a mile. The physical distance it needs to cover is so incredibly short that even with a lifespan of only 2 microseconds, the Earth easily closes the distance before the muon decays.
That is just phenomenal. If you ask the scientist on the ground, the muon survived because its time stretched out. If you ask the muon, it survived because the physical distance of the universe shrank. Both observers measure completely different times and completely different distances, yet they arrive at the exact same physical event. The muon hits the detector.
Both realities are mathematically true. The undeniable physical fact is that the muons arrive at the ground, and that absolute fact could not happen without the elasticity of spacetime.
Okay, so we've established the first mechanism, moving at high velocity warps time. But honestly, most of us aren't exactly traveling at near light speed on a Tuesday afternoon.
Yeah.
However, the universe isn't done messing with our clocks. There is a second, entirely separate force that warps time, and it has absolutely nothing to do with velocity.
Right.
It's happening right now, pulling time apart right beneath our feet.
This brings us to 1915, a full decade after special relativity. Einstein published his general theory of relativity, which remains the current standard model of gravitation in modern physics. General relativity introduced a completely new mechanism for time dilation, the presence of mass.
Gravitational time dilation. Every time gravity is brought up in documentaries, they always use the exact same analogy. The bowling ball sitting on a rubber trampoline, creating a dip that makes smaller marbles roll toward it. But I have heard physicists actively groan when that analogy is brought up. Why is it flawed, and how should we actually visualize gravity?
Physicists dislike the trampoline analogy because it uses gravity to explain gravity. The bowling ball pulls the rubber sheet down because of the Earth's gravity underneath it. It doesn't actually explain the mechanism of space-time curvature.
That makes sense. So what's a better way to picture it?
A much better way to visualize it is to imagine a 3-dimensional grid, like a massive block of translucent jelly with perfectly straight grid lines drawn through it. If you inject a massive object, like a star or a planet, into the center of that jelly, it pulls the surrounding grid lines inward toward itself. The grid lines bunch up and stretch around the mass.
So gravity isn't a magical, invisible tether pulling objects together. Objects are just trying to move in a straight line through the jelly. But because the grid lines themselves are curved toward the planet, following a straight path naturally leads them into a collision course with a massive object.
Exactly. What Newton perceived as a force pulling an apple from a tree, Einstein revealed to simply be the apple following the natural curved geometry of spacetime caused by the Earth's mass. But here's the critical leap. Space and time are a single fused fabric. You cannot warp the spatial grid lines without simultaneously warping the temporal grid lines.
So the presence of a massive object Literally bends time, just as it bends space.
That is the core revelation of general relativity. Clocks that are deeper down in a gravitational potential, well-meaning, they are physically closer to the center of a massive object, will run more slowly than clocks that are further away from the mass. Gravity slows down time.
The physical intuition behind velocity slowing down time made sense with the light clock geometry. But how did Einstein intuitively figure out that gravity slows down time? What was the thought process there?
He used a thought experiment that he later referred to as his happiest thought. It led to the equivalence principle, the absolute cornerstone of general relativity. Einstein realized that the physical local experience of resting inside a gravitational field is utterly indistinguishable from the experience of being inside an accelerating reference frame.
Let's break down the elevator thought experiment, because this is brilliant.
Yeah.
Imagine an astronaut sealed inside a box like an elevator car with absolutely no windows. They cannot look outside to see where they are.
Yeah.
Scenario 1. The box is sitting stationary on the surface of the Earth. The astronaut feels their normal weight pressing down on their boots. If they take a pen out of their pocket and let go, it drops to the floor at an acceleration of 9.8 meters per second squared.
Now consider scenario 2. Take that exact same windowless box with the astronaut inside and teleport it into deep interstellar space, light years away from any planets or stars. There's zero gravity. The astronaut is floating. But now, attach a massive rocket thruster to the bottom of the box and fire it so that the box accelerates upward at precisely 9.8 meters per second squared.
Because the floor is accelerating up to meet the astronaut at the exact same rate as Earth's gravity, the astronaut is pressed down into their boots with the exact same force. If they let go of the pen doesn't fall. Rather, the floor of the box accelerates up and smashes into the pen at 9.8 meters per second squared.
Exactly.
From the astronaut's perspective inside the sealed room, the physics look identically the same.
The equivalence principle states that no local experiment the astronaut can perform inside that box will allow them to distinguish whether they are sitting on a planet experiencing gravity or floating in deep space experiencing constant acceleration. The two scenarios are completely physically equivalent.
But how does equating gravity to a rocket engine prove that gravity bends time?
Because if the two environments are truly equivalent, any physical phenomenon that occurs in the accelerating rocket must also logically occur in a gravitational field. Think about what happens to light in that accelerating elevator.
Okay.
Imagine a laser beam is fired horizontally from the left wall to the right wall. In a stationary box, it travels in a perfectly straight horizontal line. But if the box is accelerating upward at a massive rate, by the time the light reaches the right wall, the wall has moved up.
So the light beam hits the right wall slightly lower than where it started on the left wall. From the astronaut's perspective, the light beam didn't travel straight. It curved downward toward the floor.
Exactly. Acceleration curves the path of light. Therefore, due to the equivalence principle, gravity must also curve the path of light. Now, apply this logic to time. In the accelerating rocket, the floor of the box is constantly accelerating, essentially chasing the light signal sent from the ceiling. Because of the complex kinematics of acceleration, the back of the rocket behaves as though it is moving at a different relative velocity than the front.
And we established earlier that different velocities mean different rates of time. So the acceleration forces the clock on the floor of the rocket to tick slower than the clock on the ceiling.
And the trap snaps shut again. If a clock at the bottom of an accelerating rocket runs slower than a clock at the top, and acceleration is indistinguishable from gravity, then a clock sitting lower down in a gravitational well must run slower than a clock sitting higher up.
Because the bottom of the elevator is mathematically identical to being closer to the center of the Earth. This means gravitational time dilation isn't just happening near supermassive black holes or neutron stars. It's happening constantly right here on Earth.
Oh, absolutely.
A clock sitting on the beach at sea level is physically ticking slower than an identical clock sitting in a cabin at the top of the Rocky Mountains.
The gravitational pull is slightly weaker at the top of the mountain because the summit is further away from the dense center of the Earth's mass. You're higher up in the gravitational potential well. Therefore, time flows slightly faster at altitude.
Wait, stop there. If time runs slower, the closer you are to the Earth, that means right now, as I'm sitting in this chair, my feet are experiencing a stronger gravitational pull than my head. So my feet are physically aging slower than my brain.
It sounds like the punchline to a physics joke, but it is a literal, unavoidable biological reality. Your head is roughly 5 or 6 feet further away from the center of the Earth than your feet are. The gravitational gradient across your body means time is passing infinitesimally faster for your mind than it is for your toes.
How does biological cohesion even work if my blood is pumping across different time zones?
Because, similarly to the airplane speeds we talked about, the difference in gravity across 6 feet of human height is incredibly tiny. The time difference accumulated over an entire human lifespan would amount to a fraction of a microsecond. But the conceptual reality remains. Your body is spanning a temporal gradient.
And just like the Hafele-Keating experiment, physicists couldn't resist measuring this. But they didn't go to Mount Everest. They measured the time difference across a distance so small it borders on the absurd.
You're referring to the 2010 experiment at the National Institute of Standards and Technology, or NIST, in Boulder, Colorado.
Yeah, that's the one.
By 2010, chronometry had evolved far beyond the cesium clocks of the 1970s. NIST physicists were using optical aluminum ion clocks. These devices trap a single charged atom of aluminum using electromagnetic fields and measure the incredibly rapid oscillations of its energy state using ultraviolet lasers.
A clock that relies on a single vibrating atom.
They are so unthinkably precise that they would neither gain nor lose a single second over an estimated 3.7 billion years.
That's almost the age of the Earth.
Exactly. They are sensitive enough to detect microscopic fluctuations in the fabric of space-time itself. The physicists took 2 of these aluminum ion clocks, synchronized them, and placed them in the same laboratory. But they separated them in height.
By how much? Like a few stories in a building.
By 33 centimeters, roughly 1 foot.
1 foot. A single step on a staircase.
Just a single step. And they monitored the ticking rates. The clock that was 33 centimeters higher up ran demonstrably faster than the clock that was lower down. The results perfectly aligned with the equations of general relativity.
The universe has a resolution so fine that it is actively keeping track of the gravitational time difference across the height of a coffee table.
The structure of reality is incredibly sensitive. The curvature of the universe dictates the rate of time at the macroscopic scale of galaxies and at the microscopic scale of your living room.
It's so easy to listen to all of this. Aluminum ion clocks, fractions of a nanosecond, variations across a footstool, and file it away as microscopic trivia. It's a brilliant flex of experimental physics, but it feels completely disconnected from daily human life.
But that is the ultimate illusion.
Right. The terrifying truth is that you, the listener, rely on this relativistic weirdness to navigate your day. If we ignored the fact that time bends and warps, our modern civilization would start to collapse within a few hours. Let's talk about the system that proves Einstein right billions of times a day. The global positioning system.
The GPS network is the ultimate, undeniable, practical application of relativistic physics. It's a constellation of at least 24 satellites orbiting the Earth, providing continuous location data to military assets, commercial shipping, aviation, and, of course, the phone in your pocket.
Let's break down exactly how my phone knows I'm standing on a specific street corner. How does GPS actually work?
It's a process called trilateration, and it is entirely dependent on ultra-precise timing. Every GPS satellite is carrying multiple atomic clocks. These satellites are constantly broadcasting a radio signal down to Earth.
Okay, and what's in the signal?
The signal contains 2 vital pieces of information: the exact identity and location of the satellite in orbit, and the precise time the signal was transmitted.
So my phone's GPS receiver isn't transmitting anything, it's just listening for these signals raining down from space.
Exactly. Your phone picks up signals from at least 4 different satellites simultaneously. Radio waves travel at the speed of light, which is a known constant. When your phone receives a signal, it checks its own internal clock and compares it to the timestamp of when the signal left the satellite. The tiny delay, the time it took the signal to travel from space to your pocket, allows the phone to calculate exactly how far away that specific satellite is.
Because speed times time equals distance. If I know the signal took exactly a fraction of a second to reach me, and I know the speed of light, I know I'm sitting exactly on the edge of an imaginary sphere extending outward from that satellite.
Precisely. One satellite tells you that you are somewhere on the surface of a massive sphere. 2 satellites intersect to create a circle of possible locations. 3 satellites intersect at exactly 2 points in space, and the 4th satellite eliminates one of those points, pinpointing your exact latitude, longitude, and altitude on the surface of the Earth.
But because light travels incredibly fast, roughly 300,000 kilometers per second, that time delay measurement has to be flawless. If the clock on the satellite and the clock on my phone are out of sync by even a microscopic fraction of a second, the distance calculation will be wildly wrong.
The synchronization must be maintained to an extraordinary, mind-bending level of precision. And this is where the genius of Albert Einstein collides with modern engineering. The clocks on those satellites are orbiting the Earth, which means they are being subjected to both special and general relativity simultaneously. And the two theories are pulling time in opposite directions.
This is the ultimate physics math problem. Okay, let's start with the motion. Special relativity.
To maintain a stable orbit, GPS satellites travel at roughly 14,000 kilometers per hour relative to receivers on the ground. As we learn from the light clock, high velocity means slower time. Because they're moving so fast, special relativistic time dilation causes the satellite clocks to tick slower than clocks on the ground. The math calculates that they lose about 7 microseconds, 7 millionths of a second, every single day.
Okay, so special relativity is dragging the clocks backward by 7 microseconds a day. But the satellites aren't just moving fast, they're very high up.
They orbit at an altitude of approximately 20,000 kilometers. At that extreme distance, they are significantly higher up the Earth's gravitational potential well than we are. The gravity they experience is roughly 1/4 as strong as the gravity on the surface. And as we learn from the equivalence principle, weaker gravity means faster time.
So general relativity is pushing the clocks forward.
Yes. Because they reside in a weaker gravitational field, general relativistic time dilation causes the satellite clocks to run faster than clocks on the ground by approximately 45 microseconds per day.
So we have a relativistic tug of war. Motion slows them down by 7 microseconds. Gravity speeds them up by 45 microseconds.
You combine the effects to find the net differential. The gravitational effect is stronger. The satellite clocks run fast by a net total of 38 microseconds per day relative to clocks resting on the surface of the Earth.
38 microseconds. 38 millionths of a second a day. Imagine being the project managers in the 1970s trying to build this system. It would be so tempting to look at that number and say, Einstein's theories are a mathematical headache. 38 millionths of a second is a rounding error. Let's just assume Newtonian time is universal, ignore the relativity, and launch the satellites. What happens if we ignore the 38 microseconds?
If the engineers had ignored that relativistic drift, the entire GPS network would be worse than useless. It would be catastrophically dangerous. Because the system calculates distance based on the speed of light, a timing error of a single microsecond translates to a distance error of roughly 300 meters, or about 1,000 feet.
Oh, wow. 1 microsecond equals 1,000 feet of error on the map.
If you let an uncorrected error of 38 microseconds accumulate over a single day, the position calculations would drift by more than 11 kilometers per day.
11 kilometers of error added every single day.
Every day. Within a matter of hours, your phone's GPS would place you blocks away from your actual location. By the end of the day, it would tell you to turn your car into a river or insist that a commercial airliner was miles away from the runway it was trying to land on. The banking system, which relies on GPS timestamps to synchronize global financial transactions, would desynchronize and fail. The power grid, which uses GPS to phase-align alternating current across vast distances, could experience massive cascading blackouts.
That is genuinely terrifying. Our modern infrastructure is entirely dependent on a network of space clocks that we literally had to program to tick at the wrong speed before we launched them, just so they would sync up with us once they hit the warping of orbit. We have built the curvature of space-time into our everyday tools.
Without a deep, functional understanding of how both velocity and gravity warp the passage of time, the modern world as we know it would not function. It is the most consequential daily proof of relativity in existence.
So we've conquered the microsecond scale. We've mastered the microscopic fractions of a second needed to keep our banking systems running and our digital maps accurate. But human ambition doesn't stop at low Earth orbit. What happens when we scale this up? What happens to human biology, human psychology, and human society when we push the math of relativity to the extremes of deep space travel?
When we extrapolate these equations to the macro scale, we run into the most famous and historically the most fiercely debated thought experiment in all of relativistic physics, the twin paradox.
I have struggled with the twin paradox for years because it feels like a logical trap that relativity sets for itself. Set the stage for us.
The premise is simple. Imagine a pair of identical twins born on the exact same day. Let's call them the traveler and the homebody. The traveler gets into a highly advanced spacecraft capable of interstellar travel. She fires up the engines and accelerates to a massive speed, say 90% of the speed of light. She travels to a distant star system, slows down to turn around, accelerates back to 90% of the speed of light, and eventually returns to Earth.
And the homebody twin.
The homebody stays completely stationary on Earth, working at a desk, waiting for her sister to return from the voyage.
Okay, applying what we know about special relativity and the Lorentz factor, the traveler is moving incredibly fast relative to the Earth. High velocity means time dilation. So the traveler's internal clock, the ticking of her watch, the beating of her heart, the cellular aging of her body, is running significantly slower than the clocks on Earth.
Correct. When the spacecraft finally lands back on Earth and the door opens, the math dictates that significantly less time has passed for the traveler than for the homebody. The traveler steps out of the ship physically, biologically younger than her identical twin who stayed behind.
But here is where my brain rebels, and where the paradox rears its head. Einstein's whole premise is that motion is relative. There's no absolute stationary background to the universe. If the traveler is sitting in her spaceship, looking out the window, why couldn't she just claim that her ship is completely stationary, and it's the Earth that fired invisible engines and rocketed away from her at 90% of the speed of light and then came flying back?
That is the exact crux of the problem. It's a brilliant question, and it caused immense confusion in the early days of relativity.
Because if the traveler thinks the Earth is the thing moving, then from her perspective, the Earth's time should be running slower. She should expect the homebody twin to be the younger one. Both twins have perfectly valid reasons to look at the other and say, you are the one moving, so your time is slower. But when the ship lands, they can't both be younger than each other. One of them actually steps out of the ship definitively younger. How is that not a fatalogical flaw in the theory?
It appears to be a paradox, but the resolution lies in a critical physical asymmetry between their two journeys. The principle of relativity, the idea that you cannot determine who is really moving, only applies perfectly to inertial reference frames. An inertial frame is a perspective that is moving at a steady, constant velocity in a straight line with no acceleration.
But the traveler didn't just move at a constant velocity forever. She had to turn around.
Exactly. To leave Earth, the traveler had to ignite her engines and experience enormous acceleration forces pressing her into her seat. To stop at the distant star, she had to violently decelerate. To come back, she had to accelerate again. And to park the ship back on Earth, she had to decelerate one final time. The traveler physically felt the g-forces of changing velocity.
While the homebody twin just sat in a comfortable chair on Earth, never experiencing any massive g-forces.
The acceleration entirely breaks the symmetry between the two perspectives. The homebody remained in the single inertial reference frame the entire time. The traveler, however, jumped between multiple different reference frames: the outbound frame, the turning around accelerating frame, and the inbound frame. The universe is fully aware of who accelerated because acceleration is an absolute, physically measurable experience. Because of this asymmetry, the mathematical calculations yield an absolute result. The twin who underwent the acceleration and changed reference frames is unequivocally the one who ages less.
So it's not a paradox at all. It's just a highly counterintuitive physical fact. If we ever build an engine capable of this, the traveling twin will return younger. And depending on the velocity, we aren't talking about microseconds anymore. We're talking about decades. Let's invent a hypothetical mission to truly grasp the deep space implications of this. Let's say we want to send a human crew to explore a star system that is 400 light years away. And we've engineered a ship that can cruise at 99% of the speed of light.
The math here shifts from physics to profound sociology. Let's look at the timeline from Earth's perspective first. The star is 400 light years away. The ship is traveling at just under the speed of light. Therefore, from the perspective of mission control on Earth, it's going to take the ship slightly more than 400 years to reach the destination.
4 centuries. We launched the ship, and everyone involved in the launch dies of old age. Their great-great-grandchildren die of old age. Entire empires could rise and collapse. Technology will revolutionize completely. But what is the experience of the crew inside the ship?
Inside the ship, cruising at 99% at the speed of light, the Lorentz factor is roughly 7. The time dilation is immense. For the crew, the journey does not drag on for 400 years. From their biological and psychological perspective, only about 56 years will elapse during the entire outbound transit.
56 years. A young astronaut in their 20s boards the ship, and they arrive at the destination in their late 70s. They experience a single human lifetime, while the Earth experiences 4 centuries of history.
And consider the implications if they attempt to return. If they spend a few years exploring and then fly back to Earth at the same speed, another 56 years will pass for them, but another 400 years will pass on Earth.
They will return, having aged a little over a century, but they will step out of the airlock onto an Earth that is more than 800 years older than the one they left.
They would return to a completely alien world. The language might be incomprehensible. The nations that launched them might no longer exist. Everyone they ever knew, loved, or read about would be ancient historical footnotes. Time dilation oscillates at the absolute limits of human endurance. The same mathematical principles that make a smartphone map accurate today act as a one-way time machine into the future for interstellar travelers.
It imposes a tragic quarantine on the universe. You are physically allowed to travel among the stars, but the universe demands that you sacrifice your own timeline, your own era, to pay for the ticket. The isolation is profound.
It is the ultimate boundary condition of human exploration. And we must remember, this relativistic framework isn't just a quirky hurdle for future astronauts, it's already deeply embedded in the bedrock of modern physics. In quantum field theory, which governs the subatomic realm, particle physicists deal with extreme time dilation as a routine chore. When they accelerate particles in colliders like CERN, the particles are moving at fractions of a percent below the speed of light. Their observed decay rates stretch out massively due to the Lorentz factor. The physicists have to manually correct for time dilation just to make their quantum equations balance. The theory is flawlessly robust from the scale of the subatomic to the scale of the galactic.
Okay, so we know the math is bulletproof. The GPS satellites prove the engineering works. Particle colliders prove the quantum mechanics work. The physical reality of time stretching and shrinking is undeniable. But this forces us into a very uncomfortable corner. If time runs at vastly different speeds depending on where you are sitting, how strong the gravity is, and how fast you're moving, what does that actually mean for the concept of now?
This is where we cross the border from rigid physics into the deepest, most unsettling realms of philosophy. Because relativity essentially assassinates our intuitive understanding of the present moment.
We all walk around with this ingrained belief that there is a universal now. Like, as I'm speaking these words right at this exact second, a volcano is erupting on Jupiter's moon Io, and a star is going supernova in the Andromeda galaxy. And all of those events are happening in the exact same present slice of time that I'm currently experiencing.
That is Newtonian time. It's the belief in a cosmic now that slices uniformly across the entire universe. But if time is relative, if the rate of clocks depends on motion and gravity, then the concept of a synchronized universal present cannot mathematically exist.
Because two observers can completely disagree on the timeline of events.
Exactly. Relativity introduces the concept of the relativity of simultaneity. Imagine you are floating in space and you see two distant stars explode at the exact same time. To you, those events are perfectly simultaneous. But another observer, flying past you in a spaceship at high velocity toward one star and away from the other, will see the light from the approaching star first. To them, the explosions were not simultaneous. One clearly happened before the other.
And because there's no preferred reference frame, neither observer is wrong.
Neither is wrong. If observers cannot agree on whether two events happened at the same time, then it is physically impossible to draw a single objective line across the universe and call it now. Your now is entirely local to your specific velocity and gravitational field.
If the universal present doesn't exist, what replaces it? How do physicists visualize reality if it isn't a series of universal moments clicking forward?
Many physicists are led by the equations of general relativity to a concept known as the block universe, or eternalism. It requires abandoning the idea of time flowing entirely.
Explain the block universe. How should I picture it?
Imagine a massive, solid block of transparent amber, but instead of just representing the three dimensions of space, up, down, left, right, forward, backward, this block also contains time as a physical, structural fourth dimension. In the block universe model, every single moment that has ever happened and every single moment that ever will happen exists simultaneously within this eternal block.
So the past hasn't vanished into nothingness, and the future isn't some blank, unwritten void. They're just physical locations within the block.
Precisely. Think about space. Just because you are sitting in London does not mean that Tokyo has ceased to exist or that New York hasn't been built yet. They all exist simultaneously. You just happen to be located at a specific coordinate. In the block universe, time works exactly the same way. The year 1920, the year you were born, the present moment you are listening to my voice, and the year 3020 all exist simultaneously, permanently etched into the fabric of four-dimensional space-time.
There's a quote from the brilliant physicist Herman Weyl that always gives me chills when thinking about this. He wrote, "The objective world simply is, it does not happen."
It does not happen. It is a profound summation. In the block universe, the Big Bang, the construction of the pyramids, your entire life, and the eventual heat death of the universe are all just static structures embedded in the block. The flow of time, that visceral, unshakable feeling we all have of a moving present, of sliding relentlessly from the past into the open future, might not be a physical property of the universe at all.
Wait, if the universe is static, why do I feel like time is passing? Why do I remember yesterday but not tomorrow?
The flow of time might simply be a subjective psychological illusion, a biological trick our brains evolved to process a static, four-dimensional reality one thin, three-dimensional slice at a time. Consciousness acts like a spotlight dragging slowly across the solid block of amber, illuminating one slice of space-time and calling it now before moving to the next.
That is a deeply unsettling conclusion. Because if the block universe is real, and the future is already sitting there in the amber, what happens to free will? If my choices tomorrow are already structurally embedded in the space-time block, am I actually making choices? Or am I just a needle on a record player experiencing a song that has already been pressed into vinyl?
You've hit on exactly why this is one of the most fiercely debated metaphysical topics in science. We must be clear. While the mathematics of relativity heavily imply the block universe, it is not universally accepted as the definitive truth of reality. There is significant pushback from both physicists and philosophers.
So the science doesn't mandate the existential dread just yet. What is the counterargument?
The core question is whether the physics of relativity strictly dictates the metaphysics of existence. Proponents of eternalism argue that the relativity of simultaneity leaves no other logical option. If different observers have different nows that include events in another observer's past or future, all those events must be equally real.
And the opponents, the people who still believe time is actively slowing.
They fall into camps like presentism or the growing block theory. They argue that the mathematical equations of relativity are just that, mathematical models for calculating observations. They argue the math underdetermines the metaphysics. In their view, relativity is completely compatible with a dynamic universe where the present is an objectively real, moving boundary that actively brings the future into existence. The fact that different observers measure that boundary differently due to light speed delays and reference frames doesn't mean the boundary itself is an illusion.
So we have built a flawless mathematical apparatus that allows us to sync satellite networks to the microsecond and predict the exact decay rates of subatomic particles.
Oh.
But at the very bottom of the rabbit hole, the greatest minds in the world are still arguing about whether tomorrow has already happened.
Exactly. It perfectly bridges the intense, rigorous, technical precision of physics with the grandest, most unanswerable questions of philosophy. Equations can calculate the time dilation of a muon, but equations cannot definitively answer the nature of conscious experience or the existence of free will.
To bring this massive journey all together, Albert Einstein looked at a universe that seemed chaotic and full of contradictions like light, refusing to behave like a thrown baseball. And he brought an elegant, unbreakable mathematical order to it. But the price we had to pay for that mathematical order was the destruction of our common sense.
He proved that the universe does not care about human intuition. It does not have a single master clock ticking away in the background. As the science of time dilation proves with absolute, tested certainty, the universe possesses exactly as many clocks as there are places, gravitational fields, and states of motion. Every single object, every planet, every rocket ship, every individual person, every single atom faithfully keeps its own unique time. And that time accelerates or drags depending entirely on the curvature of space-time it navigates.
The universe keeps its own decentralized ledgers, and the math allows for two people to look at the exact same beam of light, experience a completely different flow of reality, biologically age at different rates, and both be 100% perfectly correct in their measurements.
Einstein himself once remarked that the most incomprehensible thing about the universe is that it is comprehensible. Time dilation embodies that paradox perfectly. It violently violates every ordinary assumption we possess about the universality of seconds, minutes, and years. Yet we can derive it from simple geometric principles, confirm it by flying atomic clocks around the globe, and apply it with astonishing engineering precision to a satellite network that guides us to the grocery store.
The cosmos doesn't owe us a reality that makes sense to our primate brains. It operates on its own magnificent, warped logic.
And the ultimate task of science is to follow the experimental evidence wherever it leads, even when it demands that we abandon the deepest, most comforting illusions we hold about reality.
So as we wrap up, I want you to look back at the clock on your wall, the one we started this entire conversation with. It is still ticking. And it's keeping perfectly good, accurate time for you right in the specific chair you're sitting in. But remember what it is actually doing. It is keeping its own local time. Nothing, absolutely nowhere in the vastness of the cosmos is keeping universal time.
Which leaves us with a truly mind-expanding, somewhat haunting question to ponder. We discussed how the flow of time might simply be a psychological trick, a biological mechanism. Our brains evolved to navigate the static, four-dimensional block of space-time. But try to imagine a perspective outside of that limitation.
Outside the human experience.
Right. What would reality look like to a consciousness that wasn't bound by that evolutionary trick? If a hyper-advanced artificial intelligence or some radically different higher-dimensional biological entity could somehow perceive all four dimensions of space-time simultaneously, able to see the very beginning of your life and the absolute end of it in a single, unified, eternal glance.
That's a huge thought.
Would they even recognize us as living, conscious, thinking beings? Or would human lives just look to them like static, unchanging, elongated shapes frozen forever in the solid amber of space-time?